To most drivers, a highway interchange feels like pure chaos. Millions of independent actors making unpredictable decisions in real time. But for a civil engineer, that chaos is predictable. A highway functions as a pipeline, where vehicle flow is governed by the same mathematical laws as any other fluid dynamic. The foundation of this system is defined in Unit 1 of the engineering syllabus, which focuses on traffic characteristics and traffic studies. Mastering these bedrock principles is a prerequisite for more advanced work, like the road safety audits detailed in Unit 4. We cannot design infrastructure without first quantifying the biological limits of the driver and the mechanical limits of the vehicle. Traffic engineering is the process of translating those human and mechanical constraints into precise geometric requirements. To build our model, we start with the individual road user. We categorize their behavior through 4 lenses: physical, mental, psychological, and environmental characteristics. The most critical biological constraint is PEIV theory, an acronym for perception, intellection, emotion, and volition. PEIV represents the total reaction time required to see a hazard, process the information, and physically move a foot to begin slamming on the brakes. Once we have quantified the driver's brain, we must measure the machine they operate. Designing for every possible vehicle size is impossible, so engineering relies on uniform standards. These are the maximum dimensions legally allowed for vehicles on Indian roads. Specifically, engineers design for a maximum width of 2.50 meters and a maximum length of 11.00 meters for a single unit vehicle. Static characteristics like these dictate lane widths, while dynamic characteristics like speed and acceleration determine the radii of curves and the required sight distances. Every painted line and paved curve on a highway is a geometric projection of these specific PIEV reaction times and mechanical dimensions. Scaling up from a single car to thousands creates a traffic stream. We measure this through traffic volume, the number of vehicles crossing a section of road per unit of time. However, roads do not carry a uniform flow of identical cars, which makes raw volume counts difficult to use. Mixed traffic environments contain extreme disparities in size and speed, with high-speed motorized vehicles sharing the same space as animal-drawn carts. To account for this, engineers use the passenger car unit, or PCU. The PCU standardizes different vehicles into a single mathematical unit. This allows us to calculate volume accurately, whether the stream is full of motorcycles or heavy trucks. With volume standardized, we then analyze speed through 2 separate studies: spot speed and journey speed. Spot speed measures travel across a single point to design local geometry, while journey speed measures time across an entire route to evaluate network efficiency. The PCU provides the data consistency needed to turn these observations into actionable engineering designs. To collect this data, engineers must measure journey times and locate delays without halting the flow of traffic. This is done using the floating car method, where a test vehicle is driven directly within the traffic stream. Observers inside the car record specific interactions, such as the total number of vehicles passing in the opposite direction. They also calculate the net difference between vehicles that overtake the test car and vehicles the test car overtakes. Simultaneously, they record the exact time it takes to travel the route, both with and against the traffic stream. By plugging these counts and times into these specific formulas, engineers can solve for the total traffic flow, or Q. This allows us to calculate the absolute volume of a roadway by simply observing relative motion from inside a moving car. The floating car method transforms the test vehicle into an active probe, pinpointing the exact duration and location of operational delays. While volume measures the current rate of flow, traffic capacity represents the absolute maximum number of vehicles a road can accommodate. Capacity is dictated by headway, the required space and time interval between successive vehicles. This chart tracks how minimum space and time headways vary based on the speed of the traffic stream. Notice that as speed increases, the required time headway reaches an optimum point, the exact moment where potential flow is maximized. This allows us to derive the theoretical maximum capacity of a lane, where capacity is a function of speed divided by vehicle spacing. The spacing variable is the sum of the vehicle's physical length and the driver's PIEV braking distance. Because human reaction limits require spacing to increase as speed increases, there is an eventual cap on how many vehicles can move through a lane per hour. Ultimately, a road's maximum capacity is a rigid mathematical limit, defined by the biological constraints of the human brain and physical dimensions of the chassis. We have built a complete architectural model of traffic flow, starting from the individual human mind and scaling up to the absolute physical limits of road capacity. This framework shows that traffic is a manageable system when we account for its core biological and mechanical variables. But what happens when the human mind fails, or the vehicle exceeds the design limits of the road? In the next phase of the curriculum, we use these same variables to analyze systemic breakdowns and traffic accidents. We then look at how engineers deploy traffic control devices, such as signs and signals, to maintain equilibrium within the flow. The concrete and asphalt are the final outcomes of these equations, a physical environment designed to function within the